You can even set up initialization sequences. So you can select the registers that you want to use for initialization, your config registers there. You can add them into the setup list. And then if you open it, you have all of the fields already there. So what you can do, you just select the mode in which device operates, and we automatically calculate decimal values for that register.
Here we are at the stand of Embedd, a London, UK-based maker of design productivity tools. I'm here with Michael Lazarenko, the founder and CEO of the company. Michael, thanks for joining us today.
Thanks a lot for stopping by. It's a pleasure to have you.
Great. So, for anyone who's not heard of Embedd or hasn't used your product before, can you explain what it is that you do and how you make design engineers' lives easier and more productive?
Yeah, absolutely. So effectively, we are breaking the barrier between hardware and software integration in electronic devices. We simplify integration of semiconductor chips, making it a journey that's actually pleasurable. Instead of you going through thousands of pages of data sheets, figuring out some of the open source code libraries and trying to make this work, we allow you to go from a data sheet to functioning, validated code within a matter of minutes.
Okay, so taking the data sheet pain out of design engineers' lives. How do you do that?
Yeah, it's a really good question. So at the core of our product, we have data models. So we build data models for different chip classes. Then,
by a chip class, you mean?
I mean interfaces, type of devices. So let's say a sensor, I2C interface,
Yeah.
SPI interface, UART.
Yeah.
So what we do is when we upload a data sheet into the system, we identify interface that supports the device class of this chip. And based on that, we pull a data model, basically a scaffolding, a structure of all of the data points we need to be able to integrate that chip type on a software level. We then use AI and complex post-processing algorithms to take the data from data sheet and complete our model structure.
And does the data sheet have to be in any particular format?
No, that's the beauty of it. So data sheet could be anything.
Even like a PDF or?
They're all PDF, unfortunately.
Okay, yeah.
But we are able to deal with some nasty screenshots that they have there, and whatnot.
Because data sheets do not have a standard format, do they? I mean, it's how the chip manufacturer chooses to make their data sheet, isn't it?
100%. I think that's the core of the problem here, is that there is no standard in how data is transferred from the chip maker to an integrator.
Yeah.
That's why there's a whole mass of you trying to figure out how it works. Although underneath, the core principles of how chip functions and communicate on the firmware level are still the same.
Yeah.
And what we are doing is we are building standardized and stable representations of chips. And that unlocks a wide variety of applications on top of that we are building, whether that's a generation of drivers for those chips, whether that's fast validation, generation of documentation or testing. Pretty much covering all of the ground there with that source of truth layer that explains how the chip is built.
So you extract the data from the data sheet, but it's not just about kind of making that library of data. Your tool then allows the design engineer, I think, to then configure the device using that information, that digital information you've extracted from the data sheet.
Yeah, absolutely. So it's not a black box at ChatGPT where you shove a data sheet and then it gives you 1,000 lines of code and you don't know how it works. What we are doing is we are changing the way that engineers interact with data that's presented to them by chip maker. We're building an enjoyable experience. We're building a UI that has some of the developer love in it, which I think embedded engineers were lacking for a few decades.
They'll be very happy for that. Absolutely. Yeah.
Trying to build that consumer experience in the engineering workflows and make building electronics a lot more enjoyable, making it easier and more enjoyable for newer generation of engineers to build electronics.
Yeah. Can you maybe show us how what this looks like in real life?
Absolutely, let's do it. So let's build a quick case study. Imagine you are building a new IoT sensor. It has an accelerometer in it.
Yeah.
And now you need to find an accelerometer. You need to choose the one from the multiple choices that you have on the market.
The thousands, absolutely.
Let's say analog devices, ST, TDK. You have all of that on your table. You have the data sheets. How do you choose? How do you make sure that it actually works? So this is the first step where we come in. So let's actually see how it works in the system.
Yeah.
First thing you will do, you'll actually upload the data sheet for a component in question.
Yeah.
So here I upload the data sheet for this MPU 6000. And what we do, as we discussed, we take the data sheet and we extract all of that information into the digital component model. That is a configuration, meaning that you as a developer have full control over all of the data that's going to go into code. And we use no AI to generate code. All of the code generation is deterministic, meaning stable, no hallucinations, anything like that.
Yeah.
So what does it mean? It means that now it looks like a nice configuration where you can see what the device is, you can see the interface it supports, you can select the one you want to use. Let's say you want to use I2C,
Yep.
and you can select the frequency that the chip supports.
Yep.
You can select the address that is where you have that connected.
Yep.
All is pulled for you from the datasheet source. We've extracted all of the register mapping for you. So for each register here, and this device has quite a few, as we can see, you basically can expand this view and see the names, addresses, sizes, access type, descriptions, all of the bit allocations are extracted for you, constraints, values, descriptions for them. And as I mentioned, this is a configuration, meaning that you can change it, and you can change it visually. So here you're basically able to even drag and drop things and make, let's say, this additional reserved offset, market reserved, automatically that is reflected in the model. You can make any change here. On top of it, all of the data is backlinked to the PDF. So if, let's say, you're not sure what this config register does, you can click on the PDF button in the system and then turn on the backlink mode, click on the data point in question, and we'll show you where exactly that data point was taken from in the data sheet. So you have the context of it. So it's about the interaction with the data. It's not about, just spitting out thousands of lines of code and then off you go trying to figure out how it works. It's about you having a structured approach and an interface to deal with how the chip is built.
Leaving the design engineering controlled, but
exactly
much faster and easier.
And it's not just registers. We have your data types, you have events like interrupts, message types. You can open it and you can see the status register associated with pins. All of that is in the system for you. You can even set up initialization sequences. So you can select the registers that you want to use for initialization, your config registers there. You can add them into the setup list. And then if you open it, you have all of the fields already there. So what you can do, you just select the mode in which device operates, and we automatically calculate decimal values for that register. Same goes for gyro. You can just select, that precision that you want to use for it, and we'll just figure out the value for you and we'll put it in the code.
So there's a bit of design automation going on here as well. Okay.
100%. So it's just a different journey for you to deal with it.
Absolutely. And without Embedd, then this would all be being done kind of manually. The design engineer would be extracting this information manually from the PDF datasheet and then somehow making their configuration software themselves.
And then calculating binary values and figuring out how that transforms into hex. And here, for example, I can just click and convert decimal to hex in a second.
Okay. So you can do this for for any chip?
Right now, we support I2C and SPI-based devices.
Okay.
So that basically is a limitation.
But that's a really broad range of devices.
It is indeed. And then
over time, with that, you're expecting to expand that your coverage?
Absolutely. We are working on UART already. We are working on expanding types of targets we work with as well.
Yeah.
So,
and if someone wants to use your software, how is it available to them? Is it on a license basis or?
There is a free tier, and I'm going to show it to you. What is included.
Yeah.
There is an enterprise tier and testing.
So that's on a subscription basis?
So there are subscriptions that unlock additional complexities in the process. So
people can get started with it with the free version, and then if they need more functionality, they
Exactly. So one of the paid features, for example, that we are introducing is ability to test whether that chip functions in 1 minute without touching any code. So if you've just configured that chip, we are happy with that configuration. What you can do, you can say, I actually have this dev board on my table. This is a Nucleo from ST.
Yeah.
You select the board in the system.
Yeah.
You connect it. That's physically wired to my computer right now.
Yeah.
As it gets connected, you go to test. You say flash. In a matter of seconds, you basically get live readings on that accelerometer. So you can actually see if it's working.
Wow.
So you've just now, we've effectively what we've done, we've generated the driver for that peripheral based on the configuration you've made, and we've integrated it into a board support package for that board. Here it's functioning all on Zephyr.
So you've literally done that fast. That wasn't pre-set up?
No, this was done when we were
in real time.
And from here, we can go further. Let's say you're happy with this chip, it's working, you validated a bunch, because now you can, validation process is easy, because you can actually see what's working, what's not. In minutes. In a day, you can do 10 chips. But then from here, let's say you're a hardware engineer, you've tested it, this is going to go into the final design. You can ship that configuration to your embedded software team, who can open it, already configure it. You don't need to write a Excel spreadsheet saying, this is my bus configuration, these are my registers, and all of that time waste. They just open the config that was already validated, and they can tell us, okay, the actual architecture of a device. And they can specify, okay, this is going to run on bare metal. I need the code to be MISR-C compliant. These are the settings that I need to be able to, for that to function within my wider project that I'm building. And from here, we can just click generate a driver, and within seconds, we deterministically generate a driver library. So here, if I open it, bunch of files, everything you need to integrate that MPU into your device. When I said deterministically, why it's important, because a lot of people think this is an AI nightmare when all of this code and it's just, you get things or errors in places where you're not expected. This is not the case. We've used AI to structure the information we've given to you. You've tested and validated that it works. Now the code is generated deterministically. Stable, can work in functional safety environment, etc. And here, everything from your defines on data types, all of your bit allocations, quite a bit of coding, your registers, register implementation, HAL implementation, bus, everything that you need is there. Plus, imagine today we've built this, 6 months in, management comes and say, guys, we are migrating to Zephyr now because it's so much cooler. And everyone starts to pull out their hair, and it's quite a bit of a pickle. What you can do here, you can go back to the configuration that you've already validated that worked on your hardware, and you can say, okay, now I need this in Zephyr. So you just change the HAL architecture setting.
Wow.
You say, make any other change. So let's say we change the name of this register to ipXchange. And we generate a new driver for this. And within a few seconds, we now have a new driver library for Zephyr, different structure, kconfig, YAML files. And if I open register header file, can see now that ipXchange is a register. So you can see how quickly you can incorporate all of the changes in the model into code.
Okay, so it really is operating from first sort of proof of concept stage right through to to production stage, and you're supporting all the way.
Exactly, because the fact that we have a stable model underneath unlocks not only code generation, but we can generate your documentation with traceability to requirements. We can generate your testing and effectively allow you to give that full package where you go from just having a data sheet, just having an idea of maybe using this chip, to making sure that this is the one you want to use, ensuring it works, and ensuring it's integrated within your specific architecture in a matter of minutes or maybe hours, because you'll still need to read data sheet, you'll still need to figure out how the chip functions. I don't take that out of the equation. Engineers still need to be engineers. But some of the stuff they're dealing with, they shouldn't really deal with.
Absolutely. Yeah, brilliant. Thank you, Michael. So there we are, Embedd taking the tedium out of design engineering and putting some of the joy back. That's wonderful to hear. Thank you, Michael.
Pleasure. Thanks a lot.